Alright, welcome to Academic Digest class. So today we're treating sorts. And we say that sorts are irrational root numbers, or we say that they are irrational numbers of the form. I will normally say that if it is carrying this kind of, let's say, root A, or let's say number inside, that this is called a quadratic sort. While if it's carrying, let's say, 3, this is called a cubic sort. So those numbers, we know that when you take the square roots, first of all, it gives you non-recurring decimals. Things like root 3, root 4, root 5, they are sorts. And we say that a perfect sort, or a sort in its basic form, is a sort without a perfect square inside it. What do I mean by that? If I have root 2, root 3, root 5 prime numbers, when they are carrying this box, this radical, we'll say that they are sorts in basic form. But when I have something like root 12, you can see that inside this I have 4 times 3, and this 4 is a perfect square because this can be the same as saying, see that this gives me 2 root 3. So a sort in its basic form is 1 in this form. Alright, let's try to solve these questions before us. And we know that irrational numbers are part of the number systems we've treated. So you can check our video on irrational numbers proper. So I have root 3, I have root 12. And root 12 is the same thing as saying 4 times 3, 12. Take the square root, so we get 2 root 3. So for I think the best way to go about this whenever you see this is to first of all ask yourself, what are the things that can divide 72? If 2 go into 70 is 35, 2 go into 2, 36. So 2 here, 36. Then 2 here, 18. Yes. 2 here, let me be sure. Yes, 2 here, 9. Can 2 go again? No. 3 here, 3. 3 here, 1. So I can see that inside this I have 2 times and 9. So this is something I'm saying 8 times 9. So 8 times 9 gives me 72, which means that root 72. So which means that root 72 is the same thing as saying 8 times 9. And you can see that this is the same thing as saying root 4 times 2 times 9. And this is the same thing as saying root 4 times root 2 times root 9. This is the same thing as saying 2 root 2 times 3. Because square root of 9 is 3. So this is going to the same thing as saying 6 root 2. So let's go to the next one. 405. 405. So ask ourselves, what can divide 405? Let's start there. So I can see that 405. So let's say I do, since the last value is 5, let's say I do 405. Since the 5 is a prime number, so I need to divide it by 5. Divided by 5, I get 81. And I know that what can go inside 81? I know that 81 can be divided by 3 to give me 27. And 27 can be divided by 3 to give me 9. And 9 can be divided by 3 to give me 3 here, 1. So let's go. I have 3 times 3 times 3 times 3, which is 81. So it simply means that 405 roots, this question, roots 405. Roots 405 is the same thing as saying, always think of this way. If you don't think this way and you're doing magic or trying to punch it with calculator, you end up not doing what is expected. So this is the same thing as saying 81 times 5. And this is something I'm saying root 81 times root 5. And you know that root 81 is that is 9 times 9 is 81. So root 81 is 9 times 5. So root 5. Are you seeing it? So this is my answer. So let's go again. Okay, here I have root m times root m. Is the same thing as saying root mn. Root m divided by root n is the same thing as saying root m over n. You see it? So this is m over n. Some books you see it as the same thing as saying root m over root n, and it's the same thing as saying root m over n. So it's the same thing. So I have x root a plus y root a. Since this is a and a, I can simply say x plus y all root a. Because check it out. If a root a go here, you have this. Root a go here, you have this. The same thing with this. You can have z minus c all into root a. Then root a plus b. This is like using it to illustrate. It is not the same thing as saying root a plus or minus root b. They are not equal. They are not the same thing. I see it. Because for example, let's say this is 3. Let's say this is 2. 3 plus 2 is 5. Now let's say I have root 3 plus root 2. Notice that this and this, by the time I do the root of this on my calculator, do the root of this on my calculator, add it up, it will not be equal to what you get from doing this. I see it. So they are not equal. Alright, they say describe similar sorts. Describe similar sorts. A sort is said to be similar if what is inside the root is the same. So if I have 2 root a, I have 88 roots a. I have minus 3 roots minus roots 3 minus root a. Then let's say I have 2 here minus 2 roots a. Then let's say I have plus 81 roots a. Provided that what you have inside the root is the same, you can add this or subtract. They are the same. They are similar sorts. So you can add or subtract similar sorts. But if, for example, I have, let's say, root a plus root b, I cannot add these two things. I cannot add it. They are not similar. So I cannot add. So cannot add or subtract them. I just leave the answer like this. You need to know this. If they are not the same thing in the roots, don't add or subtract. It's different from when it's multiplication. For multiplication, you can multiply everything, do anything. But when it's addition and subtraction, if you see that what is inside the roots, the radicals are not the same, do not add, do not subtract. Now, the next question said, to add or subtract sorts. So this is like something you need to note. Anytime I want to add or subtract sorts, for me to be sure of what I'm doing, I need to reduce them to their basic form. Basic form is simply make sure that anything that is a perfect square there gives you the number that it is, that it is the square, that is its, should I say, its square root. You understand? So for example, let's say this root 32 minus 2 root 128 plus 3 root 50. Before I can subtract or add this, I need to be sure of the things inside this. Anyone that is a perfect square will take it to give me what it really is. So let's try to solve. I have root 32. And this is the sentinel saying what and what is inside 32. Let's bring it. I don't do it with my head. I normally bring it on 32. What's the LCM? 2 into this. You can see that this is going to be 16. 2 into this. This is going to be 8. 2 into this 4. 2 into this 2. 2 into this 1. I'm trying to be very sure these days because all this doing a lot of video makes you get so filled up in the head. So I have 2 times 2 4, 4 times 2 8, 8 times 2 16, 16 times 2 32. So you can see that this is, let me group it, this is 2, this is 2, this is 16. 2 times 2 times 2, 2 times 2 raised to the power 4 is 16 times 2. So this is the sentence saying root 16 times 2. Alright. Now for roots, what else is there? Okay, 2 root 128. 2 root 128. Let's check what is inside 128. Let's get the square root, the LCM of 128. So 126, 64. Okay, 2 here, 64. 2 here, 32. 2 here, 16. 2 here, 8. 2 here, 4. 2 here, 2. 2 here, 1. Alright, so you see I have 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. 32. 64. 128. So let's group. Let's see what we have. So actually, I have 16. I have 16 times 4 times 2. So I tried to make it in such a way that all the perfect squares are single letter. So this is 2 in 4 places, and this is 4, then this is 2. So the sentence is saying, this is the sentence saying root 16 times 4 times 2. Understand? So if I know that, let's be sure. So we don't have, so 16 times 4 times 2. Yes. So let's move. We move. Let's go again. Remember that everything is carrying 2 outside. Alright. So remember this is carrying, this is 2 root 128. So let's go for the next one. 3 root 50. So 3 root 50. This is the sentence without even doing anything like solving. This is a favorite. So this is the sentence in 3 roots 2 times 25. Alright. Notice that everything in the first place gives me 4 root 2. That is square root of 16, 4. So in this next stage, which is this, I'll have 2 square root of 16 is 4. Let's go this way. 4 square root of 2 times square root of 4 is 2. Then root 2 equals to 3, 2. So root 2 times 5. So this is the sentence saying 4 times 2. Sentence saying 8 times 2. 8 times 2 root 2. Then 4 root 2. Then 3 into 5 root 2. So notice that is what you have. So if you're factoring it out now, let's check. Notice that this is root 32 minus, so everything for root 32 will give you 4 root 2 minus everything for 2 root 128 will give you 16 root 2, and everything for 3 root 50 everything for 3 root 50 will give you 3 2 plus 15 root 2. So see that we've been able to do this, and you can see clearly that they are similar sorts. Their roots are the same. So I can just add up. I can just bring out the root 2, then add up. So this is going to be 4 minus 16 plus 15. So which is the same thing as saying, let's do the maths. So 4 minus 16 plus 15. You're kidding me? So that's the same thing as saying 3 root 2. So this is going to be 3 root 2 as my answer. Okay, let's move to the next question. Next one says 3 root 18 plus 5 root 27 minus 7 root 8 minus 4 root 2. Remember the principle. Always reduce to basic form before operation, that is before subtracting or adding. So let's try to reduce to basic form. 3 root 18. 3 root 18. First of all, let's bring it out. We have 3 root 18 plus 5 root 27 minus 7 root 8 minus 4 root 2. So let's try to solve. 3 root 18. 18 first of all. 2, 9, 3, 3, 3, 1. So 9 times 2. This is something I'm saying 3 into 9 times 2 plus 5. Okay, let's check. 27. I think we've done something of 27 before. But let's do it again though. So if I have, remember that this is where we are, 5 root 27. So if I do 27 divided by 3, I get 9. So 27 divided by 3, I get 9. 3 into 9, I get 3. 3 here, 1. So 3 times 3 raised to the power 3 is 27. So I can see that this is the same thing as saying, watch. So this is the same thing as saying I have this to be the same thing as saying, let me just rewrite it, because yes, let me just rewrite it. Since 27 gives me 3, root 27 gives me 3, so let me just rewrite it. What am I saying? Cube root of 27 is what gives me 3. Cube root of 27 gives me 3, not the square root. So since it's square root we are using here for sorts, since it's square root we are using, let's just leave this as saying 3 times 3 times 3, which is the same thing as saying 9 times 3 minus, this is the same thing as saying 7 root 4 times 2 minus 4 root 2. Now notice that this is going to give me the same thing as saying everything here is going to give me 3, then root 9 is times 3 root 2 plus 5 root 9 times 3 root 3. So 3 root 3 gives me it gives me the value for this. And you remember that I said that cube root of 27 is what it gives you. So we are focusing on using this root. So don't try to play smart. Minus 7 root 4 2. So what sort helps us do is it helps us avoid those non-recurring decimals. It helps us avoid all those going forth and going backwards with decimals. So we just limit it. So this is going to be the sentence. Bring 4 root 2 down. So 4 root 2, I bring it down. So you can see that all the ones that have root 2, first of all, let's do this. This is the sentence saying 3 times 3 is 9 root 2 plus 15 root 3 minus 14 root 2 minus 4 root 2. So this is the sentence saying all the root 2's are similar sorts. So just bring them together. So I have root 2. So I see 9 here. Before this one, I see minus 14. Then before this one, I see another minus 4. Then I now have plus 15 root 3. So let's do it. Let's try to get let's try to get 9 minus 14 minus 4. I have minus 9. I have minus 9. So minus 9 root 2 plus 15 root 3. And you know that this is the sentence saying 15 root 3 minus 9 root 2. This can as well be my answer. Understand? So keeping the minus inside so that positive starts it. So let's move and see the next question we have. We have multiplication of sorts. So I very well see that we are done with addition of sorts. So the principle of addition and subtraction is simply make sure that similar sorts is what you are adding. If they are not similar, don't add it. If they are not similar sorts, do not add or subtract. You only add or subtract when they are similar sorts. And remember what we said about similar sorts. Look at it here. Things. When the roots are the same, you add. If the roots are not the same, you don't add, you don't subtract. So, but for multiplication, you don't do anything like similar sorts. You multiply everything. So this is area for multiplication. So I have root 45 times root 28. For root 45 times root 28. But the principle that remains the same is try to break it down. So 45. What are the things inside 45? Let's try to see if 5 divides 45, I'll have 9. So that means that inside here I have 9 times 5 times, what are the values inside 28? I know that 28 divided by 2 gives me 14. It's not perfect enough. Let's say I do 20. Okay, let's do it this way. Let's use our principle. Let's not do big boy or big girl. So this is 2 into 28, 14. 2 into this, 7. 7 here, 1. 7 is the prime number. So this is 7 times 4. 7 times 4 gives me 28. So this is the sentence saying 7 times 4. So 7 times 4. And this is going to the sentence saying root 9 times root 5 times root 7 times root 4. And this is the sentence saying 3 root 5 times root 7 times 2. Are you seeing it? So you can very well see that this is now the same thing as saying, I told you multiplication does not do similar. So you can just multiply through. So you can see that the roots will come and multiply each other. So we now have 3 times 2 one side. Then root 5 times root 7 one side. So that we now have 5 times 7 is 35. So we now have roots 35. Then 6 is my final answer. So we now have 6 root 35 as your final answer. Very simple. So for multiplication, there's nothing like similar sorts. But when you're doing addition and subtraction, a plus b, like this, cannot be equal. Cannot, like root a plus root b can never give you this. It's not possible. So you don't add it up. You just leave it the way it is. The same thing with the subtraction. All right, let's move to the next question. So for the next question, we have root 3 raised to power 3. Okay, this is a simple question. Some of these questions I will be leaving it out, so you have something to solve. We're going to the ones that are very hard. You solve the simple ones. So notice that this is something that's saying root 3 times root 3 times root 3. And notice this is the sentence that's saying bring out 3 times 3 times 3. This is the sentence that's saying root 27. Root 27. And you know that inside this we have 9 times 3 inside here. So this is the sentence that's saying 3 root 3. Okay, let's move to this one. Okay, this one, do this one for me as your assignment. Let me look at this one. So I have 3 plus root 2. Then I have 3 minus root 2. This is what we call conjugate surds. Whenever you have the same sort, but the only difference is the sign, and they are multiplying each other, we'll call it conjugates. So it's going to give me, at the end of the day, why we call it conjugate is that the answer I will get here at the end of the day is no longer going to be a rational number. It will now be a rational number. And you know that rational number is the one that gives you the recurring decimal. Or we say that rational number is simply numbers that are ratios of integers. That is, numbers that have numerator and denominator, whose denominator cannot be equal to 0. Or we say that they are, we can consider it as real numbers or natural numbers. So whatever we get from here will no longer be a rational number. See what I mean? This will come and do 3 into 3 minus root 2. Then plus root 2 into 3 minus root 2. So this is going to give me 9 minus 3 root 2 plus 3 root 2. That is this times in this minus root 2 times root 2 is the same thing as saying root 2 square. And this will take care of this so that I have 2. Now notice that this is minus and this is plus 3 root 2. 3. Remember that if I have 2x minus 2x, this will become 0 because they are the same thing. And minus 3a plus 3a, this is 3a, 3a, they are the same, 0. So this is going to be the same thing as saying 0 minus 2, 9. So 0 does not have minus or negative. We know that 0 is a whole number discovered by the Arabs in 632 AD. So this is going to be the same thing as saying 9 minus 2, which is the same thing as saying 7. So you can see this is the answer we have. So that is why I said we'll call it conjugate, because it will definitely make it such a way that you no longer exist with irrational number. You'll come back to the world of what we call rational numbers. Every natural number is a rational number. Every natural number is a rational number. What do I mean? 7 standing on its own is the same thing as saying 7 over 1. And we remember that rational numbers are ratios or ratios of integers, or you say numbers with denominator and numerator. So anytime you multiply conjugates, you get a rational number. Alright, so let's move to the next question. Okay, so they said, what is conjugate sorts? Conjugate sorts. What is conjugate sorts? Okay, I don't know how to put it, but I think the best way to put conjugate sorts is simply by saying the same, or you say there are sorts. There are two sorts separate with positive and negative signs. So when you have the same sorts, but the only difference is simply in their sign. So in mathematics, we don't speak GST. So as I'm speaking all this grammar, it might be confusing you. But whenever I have A plus B and I have A minus B, remember that it has to do with roots. Notice that everything here is the same thing. The only thing different is the signs. This is what we call conjugate sorts. And the concept of this answers this question. They say state and illustrate two major rules for division of sorts. The two major rules of division of sorts is simply whenever we have a denominator and that denominator is having roots, it is not proper that we leave, let's say we have root A minus B. It is not proper that we leave denominator roots at the denominator. So we simply employ the concept of conjugate and what we call rationalization. So that is the two. We apply the concept of conjugates. Here now we say, since this is root A and minus B, we know that by the time we bring a positive value that will multiply this multiply this, we know that conjugates will always make for rational number. That means it will make the surd to live here, to leave the denominator, because denominator is not supposed to have surd. So once we do this, we now employ the concept of rationalization, which is doing it for the numerator and doing it for the denominator. Whatever we do for the denominator, we do it for the numerator. That is what we call rationalization. Rationalization of sorts. So the two principles we employ when doing division of sorts is simply what we call conjugate of sorts and rationalization of sorts. Do rationalization, do it for the numerator as you did it for the denominator. And why did you do it for the denominator? Why and what did you do for the denominator? You did conjugate of sorts for the denominator in order to make sure that sort is not found at the denominator. So that is it. So let's move to the question right here. They said simplify root 8 divided by root 9. So this is going to be the same thing as saying, so I'll just do this, you do this, you do this. So root 8 divided by root 9 is the same thing as saying, what are the values inside here? Always remember, before you do sort, take it to its basic form before you do anything sort, times 2. Then this is divided by 3 times 3. And this is the same thing as saying 3 though. So which is root 9 is the root of 9 is the same thing as saying 3. Sorry, thinking too much. Divided by, this is root 4 times root 2. So 2 root 2 divided by 3. So this is going to be the same thing as saying 2 root 2 over 3. So notice that they have nothing in common. So this is my final answer. Very simple like that. This is my final answer. So let's move. Let's see if there's anyone there. So you are solve this one for me. Solve this one for me as your assignment. So let's move to this one. Okay, this one is also simple. You saw, okay, it's not, because it has that concept. So notice I have here, question 10, I have 3 over root 5. And this is the sentence I say, sort cannot be at the denominator. So I'll simply do times root 5 all over root 5. So you can see that once the two sorts multiply each other, it will now give way. So this will go up at the numerator. I'll have 3 root 5 all over root 5 square. And notice this will cancel this, so that I have 3 root 5 all over 5. So let me solve this one. I'll solve this one. Then you solve this one as your classwork. So I have 1 over 1 minus root 2 minus 1 over 1 plus root 2. So applying the principle, I have minus here. Before I solve anything in sorts, I must reduce to basic form. So I will do 1 over. It's an abomination for denominator to have roots. And notice that it's having a minus sign here. I'll simply do 1 minus root 2. Solve for this part first, then come and solve for this part. So times 1 plus root 2 all over 1 plus root 2. The reason why I'm doing this is so that these two will make room for rationalization, so that this will get out, this sort will leave here. And I cannot do it only for the denominator. Whatever I do to denominator down, do it for up. So you employ conjugate and rationalization. So see that up here, anything times 1 is going to give me the sentence. So up here I'll simply have 1 plus root 2 all over. This principle of sorts, with time there's a trick I will teach you, but for now let's do it this way. 1 into 1 plus root 2 minus 2 root 2 into 1 plus root 2. Now notice that this is going to be the same thing as saying 1 plus root 2 all over, everything here will be 1 plus root 2 minus that is 1 times this will give me everything here. And when I say this root 2 times 1 is the same thing as saying minus root 2, then minus root 2 times root 2 will simply give me minus root 2 square. And this will cancel this, so that I now have this to be the same thing as saying 1 plus root 2 all over plus root 2 and minus root 2 will become 0. So it will be 0. So which means that I'm left with 1 minus 2, which is the same thing as saying 1 plus root 2 all over minus 1. So see what I wanted to show you. Anytime you want to multiply conjugates, instead of suffering yourself to come and be doing this thing, simply carry the first value there, bring it out. Just carry the first value, as I'm seeing these two first value, bring it out. Then the second value like this, look for the sign before it is minus. So root 2 times root 2 will give me 2, just like that. So when you are multiplying conjugates, just use first term multiply first term, second term multiply second term, so that you rest, because the two in the middle will definitely give you 0. So for this part, I have, let me do it this way. So I have 1 all over 1 minus root 2, giving me 1 plus root 2 over minus 1. So let me try to solve for this one. Let me try to solve for this part before I now come and subtract. So I will now have 1 over 1 plus root 2 times 1 minus root 2, rationalization and conjugate, 1 minus root 2. So you see, I just have this is going to the center and saying 1 minus root 2, that is this times this, all over, carry the first term 1, carry the second term minus 2, root 2 square, which will give me 2. So this is the sentence saying 1 minus root 2 all over minus 1. So carry it down. So I'll bring it down. Remember that we have these two, this one minus 1 over 1 plus root 2. So when I do this now, when I subtract these two now, is the sentence as saying what I got for this minus what I got for the second one, which is 1 minus root 2 all over minus 1. So first of all, this thing now, without stressing myself, if this divides this, is the sentence as saying minus 1, that is, yes, so minus 1, yes, minus root 2. Yes, in fact, if it will stress me, I can just say, see that if minus come here, yes, minus, or if this will stress me, if this approach will stress me, I can just choose to say, let me not even do this thing like this. Let me just say, okay, let me just say, but I think it's proper I do it that way. Plus, so this one now will be the sentence as saying minus 1 minus root 2. So I have minus. So this is the sentence as saying minus 1 plus root 2. So minus 1 plus root 2 minus plus 1 plus 1 minus root 2. Wait. But notice that if this minus, first of all, I'm coming. If this minus, what am I doing? Okay, see, I'm trying to open this bracket. I have minus already here, one side. So if this minus is coming here, it will make this to be minus. To make this to be minus plus root 2. Oh, wonderful. So I have 1 plus, see where we started this madness, root 2 minus 1 minus root 2 all over minus 1 all over minus 1. So I think this thing that we're doing here, where I'm trying to explain everything as if it's English, sometimes I put myself in trouble, because what I'm supposed to do is to simply say there's minus sign between the two. That means that minus minus, and that means that this has to be LCM minus 1. So which means that by the time this divide, this becomes bring down everything. That is seen. If this come here, it will cancel, bring this down. If this come here, it will cancel, bring this down. So this is going to simply be minus root 2. And notice that if that is the case, I now have what? I now have, if I divide this by roots by minus 1, I now have 1 plus root 2 one side, then 1 minus root 2 one side, and there's minus here. This becomes alright, see, minus, this is minus, remember this is minus. If this is minus, it covers for everything here, and not just this one. Covers for everything here. Covers for everything here. So which means that this is going to be opening this, so that the minus affects everything. Since it's minusing everything, opening this up at the numerator part, I'm supposed to have minus 1 plus. So you see it. So that is where we started having issue from. So 1 plus root 2, yes. So 1 plus root 2, yes, all over. So let's do the numerator part first. So you see that I will simply have 1 minus 1, 0. Then I have plus root 2, root 2. Plus root 2, root 2. That is, see what I have. I have supposed to be minus plus all over minus 1. So I'm supposed to have, as I'm opening it up, I've opened it up, this will leave. So this is going to be 1, focus here, this is going to be 1 minus 1, 0, root 2 plus root 2, x plus x is 2x, so it's going to be 2 root 2 all over minus 1, and it's going to be the same thing as saying minus 2 root 2. That's my answer. So notice what happened. What happened is that when we have this, as we have this minus, this minus is minus everything here. So the point, at the point where we got this value, to be 1 minus root 2 all over minus 1, that is 1 minus 1 minus root 2 over minus 1. We were treating it as though the minus is only for this one, but it's not supposed to be so. It's supposed to be in such a way that I have this way, so that by the time you open this bracket, you have the minus 1, the plus root 2, and you know that there's already minus 1 at the denominator. So if you share it, don't tell me that how come it did not affect the denominator. Notice that if I have 1 minus 1 times this, it will go and affect what is at the numerator and not the denominator. So that is why I have this. So you see, it's not just about sorts. Some cases you have complex issues with signs like this, so you need to watch your sign. Make sure that whatever you're doing, you are relating it in such a way that it has to do with everything you're given. So I have a question here. They said express 2 root 3 minus 3 root 2 all over 2 root 3 plus 3 root 2 in the form a plus b root c, where a, b, and c are integers. So let me write so once I see this kind of question, they said I should do this in the form of a, I should express it in the form of a plus b plus c, where a, b, c are integers. So integers are negative whole numbers, 0 and positive whole numbers. So this is simply going to be the sentence as saying applying conjugates then rationalization, doing it for the numerator too. So I simply come, as I'm seeing this now, what I will simply do is to say 2 root 3 into 2 root 3 minus 3 root 2. Then minus 3 root 2 into 2 root 3 minus 3 root 2. All over, just come. Don't bother doing the sentence. Just the first term, multiply the first term. Second term, multiply second term. That is, here you have the same sign, but here you have different sign. Once the signs are different, so I'll just say 2 root 3 times 2 root 3. Then this minus 3 root 2 into 3 root 2. So this is going to give me, the first part I have 2 root 3, 4, 4. Then times 3 minus 6 roots. 2 times 3, 6 minus 6 roots 6 plus 9 root 2 square is 2. It's over 4 times 3. Root 3 square is 3 minus 9 times 2. Root 2 square is 2. So you see that I have 12 minus 6 root 6 minus 6 root 6 plus 18 all over 12 minus 18. So I now have 12. This is root 6, this is root 6. They are similar, so they can apply the same principle. Minus 6 is minus 12 root 6 plus 18. That is 12 minus 18 is minus 6. Should be? Yes. So we can very well see now that this is the same thing as saying 12 over minus 6, then minus 12 root 6 over minus 6 plus 18 over minus 6. The LCM is 6. And when you do the maths, it still gives you this. So this can go here, 2 go here, 3. In fact, you get 2 go here, 6, 3 go here, 1, 3 go here, 2. 6 can go here to give me 2. Yes. Even the minus. So even the minus can be taken care of since they are both minus. Now over here, 2 go here, 3, 2 go here, 9, 3 go here, 1, 3 go here, 3. So I now have 2 minus 2 plus 2 root 6 minus 3. Let's see it. And remember the question said that we should express what we have in the form of a plus b root c. Okay. Now we should express what we have in the form of a plus b root c. So which means that, notice that this is a number, this is another number. So I can have minus 2 minus 3 plus 2 root 6, which is the same as saying minus 5 plus 2 root 6. Since they want us to express this in the form of a plus bc, so this everything here can be a plus b root c. So that means that c is equals to 6, b is equals to 2, and a is equals to minus 5. That's what it means. So if we're expressing in this form, notice that we've gotten the same thing. So we got minus 5 plus 2 root 6. So we've solved it. So that is for that. So the next question is telling us to evaluate root 5 plus 2 root 6. So this one, you take it as your assignment. I'll just solve these two. I'll solve this and this. You solve the rest. You understand? Alright, let's try to look at it. So I have root 5 plus 2 root 6. The root, whenever I'm asked to find the root of a surd, automatically what I need to do is to make it in such a way that I am thinking of this first part to be A and this second part to be B. And this part in terms of C, root C. If you remember what we did earlier, the question we just finished solving. So I need to always think of it in that form. So I can just say let everything there be equals to A plus B. So I will always, whenever I'm doing this, they tell me to evaluate root 5 plus 2 root 6. I will always try to make it in such a way that I will have this A, B root C. And notice that if I choose to use this, is a good concept. But notice that root 5 plus 2 root 6, if I decide to say let it be equals to x plus y, or let's say A plus B, by the time I take the square of both sides, By the time I take the square of both sides, this will cancel this. So that I now have 5 plus 2 root 6 equals to, and notice that if I take the square of a plus b raised to power 2, it will give me something that will look like this. Let's check. Let's say I have a plus b, a plus b, a square, then plus ab, then plus ab plus b square. You see that this is the same thing as saying a square plus 2ab plus b square. So notice that this is now going to be the same thing as saying a square plus b square plus 2ab. So you can see that they look alike. You can see that they look alike. So the only difference is that the left hand side, which is 5 plus 2 root 6, that is what we started with, was carrying this. So in equality of sorts, what we are trying to do with this is simply, as we have this plus this, how do we make it? We made it to be equal to a plus b squared, because we know that at the end of the day, this is what we are trying to get whenever we have such a sort. This is a principal method. So we can now say, let's make the left hand side and the right hand side to be equal by taking the square roots of the right hand side. See that if I take the square root, this will cancel this will cancel this, so that I have a plus b, then this will now be plus root 2 root ab, 2 root a b. So remember I'm trying to get it in such a way, we've already taken the square, so I'm trying to get it in such a way that what I have on this left hand side, which is 5 plus 2 after I take the square, and yes, this will cancel this. So yes, I can see that what I have here now looks perfectly like this. So I can say that everything here looks like this one, and everything here looks like this one. Sorry. So we can say that a plus b is exactly like 5, and 2 root ab is exactly like 2 root 6. I think it's better this way. So you can now see that this is the same thing as saying, if I want to make any of these such as the form, this is the same thing as saying a is equals to 5 minus b, or b is equals to 5 minus a, depending on whichever one I choose. And I can say that AB is equals to 6. They occupy the same position. Is equals to 6. So I can go on to now say let's make this an equation. Let's make it something of an equation. So you can see that if this is AB cos 6, this can be something as saying A and this can be something as saying A5 minus, or you say 5A. I don't like doing equation 1, equation 2. Most of you, once you see all those things, you get scared. So you see at this point, these two look like something, this looks like something. So I I can make any of this my subject. So 5a, then a square equals to 6. Notice that this thing is something I'm saying a square, that is minus a square plus 5a minus 6 is equals to 0. This thing looks like something we know. If you look at it very well, it looks like what we call quadratic equation. I don't like this minus that is here. This minus. Let's say we made this to cross over this way. Let's say we made it cross over this way. Notice that this could have become, this could have easily become, crossing over this way, could have easily become 6 minus 5a plus a square equals to 0. So I want to work with this. So this is the sentence I'm saying a square, so I ignored this. So this is a square minus 5a plus 6 equals to 0. So I can solve the quadratic equation and get my final answer. But notice something. Notice the principle. The principle, first of all, whenever you are to evaluate a surd that has a square root, is simply, even without doing all these things we did here, is simply, how do I get this? How do I get this set up? That's just what we try to do. How do I get the setup? That is a plus b. And in this case, since we are using a plus b, we now took we said, this is the sentence I'm saying, we said a plus b. We now gave it roots. We gave it roots. So the sentence I'm saying, since this part has roots and this part has roots, we say everything here to be equal to this. So when we take this root of both sides, we take the square of both sides, you see that we now have a plus b, then like, see what I mean? We take the square, this becomes root a plus b, root a plus b. So whenever you see the roots of a root, you simply equate it to what we call equality of surd. This is a formula. So we are trying to do it in such a way that what we have on the left hand side, since this is having roots, this one have roots, this one is having roots, this one have roots, how do we clear up the square roots? It's simply by taking square of both sides. And once you take the square of both sides, the left hand side becomes this. Then if you solve this now, you see that this is going to be the sentence I'm saying a plus b root a. This will be plus b root a. Then this will be plus b. Okay, remember this is root 2. Am I kidding? Are you kidding me? So this will be root b, root a, root b. And this is going to be the sentence as saying root ab plus root ab plus root b. But notice that by the time root b times root b square, which is going to give me b plus a. So this is going to be root ab plus root ab is going to give me 2 ab, and it's carrying roots plus a plus b. So we simply bring out the a plus b, then plus 2 root ab. So we now say that the a plus b will now be equal to that particular one, which is this, that is not carrying this kind of attachment. So why everything here is the second part, so we now equated it to, this is the sentence as 2 root 6, this is the 6, this is the 2. So everything here is now equals to 5 plus. So when we did it, we now said if that is the case, a plus b is equals to 5. Then 2 roots ab is equals to 2 root 6. Are you seeing it? So we now said if this is the case, 6 root 6, that is 6 itself, root 6 is equals to root AB, which means that 6 is equals to AB. What is inside? So this is what we are now using to solve. So we are now saying that if AB is equals to 6, let's say I have A. Notice that this part is also the same thing as saying A equals to 5 crossing over minus B. So this is the same thing as saying 5 minus B equals to 6. This is a formula, like a pattern. Once you see that there is a root, that a surd is inside the root. Just like when you are doing complex number, you know that anytime you see negative number inside the roots, you use methods of complex number. So whenever you see a surd inside another surd, you use this approach of saying let it be equals to A plus B. That's taking the roots too. So this is going to be the same thing as saying in this case A watch, remember we did minus, so this is going to be the same thing as saying A5 minus, are you kidding me? Let's check. Yes. See, B, this is B, A now, yes, but this part is B, this part is B. So this is supposed to be B is equals to 5 minus A, so that we can substitute for B this value. So 5 minus A. So we have A5 or 5A, then A square equals to 6. So now that I have this, I can say crossing equality sign. This is going to be the same thing as saying, because I don't want to have the minus, this is the same thing as saying minus A square plus A5, 5A minus 6, but not equals to 0. But notice that assuming I did it crossing equality sign the other way, this thing can be the same thing as saying A square minus 5A plus 6 equals to 0. These two are the same thing depending on what you want to work with. So solve the quadratic equation.